Hello, everyone. I want to start by thanking Materials Square for the opportunity to talk about some of the recent work we've been doing in my group to accelerate discovery of materials and molecules through human AI machine collaboration. In this context, machine refers to robots. So basically, what we want to do is to reduce the time to solution in materials research. Now, you may wonder, why do you want to reduce the time in materials research? Well, if you look at the biggest problems that we're currently facing around the world, from renewable energy to sustainability to health equity, you soon realize the way we have conventionally been doing materials discovery and materials research has been extremely slow, expensive, and resource intensive. So, for example, in the renewable energy, it took us more than 50 years to discover an alternative to silicon. Perovskites are not even commercialized yet. But that's like tens of thousands of researchers around the globe working on one single material problem, and tens of billions of dollars of R&D just invested in solving one problem. And sustainability is the same problem. If you want to make an existing manufacturing process more sustainable, or if you want to discover a new, more sustainable manufacturing process, that's going to take you 5 to 10 years, more than $100 million of R&D. In healthcare, going from discovery to market, that typically takes more than 10 years and more than $1.2 billion of R&D. So now the question is, why is our material discovery and molecular discovery so slow and expensive? Well, one part of the problem is when you're looking for a new material or molecule, you're dealing with this infinite chemical and material universe. Unfortunately, we don't have a map of this infinite universe. So most of the time, when you're looking for a new material or molecule, you're just blindly searching through this universe. So that's 50% of the problem. The other side of the problem is the way we approach this exploration of this infinite universe. This is the current way we do material and molecular discovery. We send our highly trained scientists in the lab, and they spend 70–80% of their time just doing repetitive tasks. At the end of the day, they go back in their office, look at it 1, 5, 10 different experimental data they've generated, and then they mainly use their intuition to make a decision about the next experiment to run. So there's this large time gap between running an experiment, characterizing the compound that you have made, and then making a decision about what is the next experiment to run. And most of the time, we are working on high-dimensional problems. That means we have multiple different inputs that you have to tune to make a material molecule. So this is the other 50% of the problem that makes a material molecular discovery extremely slow, expensive, and resource-intensive. So looking at this picture, there's a lot of room for improvement. For example, we can leverage the recent advancements in robotics and lab automation to develop this end-to-end automation workflow so that we can accelerate our experimental throughput. We can go from a few hours a day to 24/7, and we can gain accelerations or increase in throughput by a factor of 2 to 10x. So that's great. Now, the question is that going to be enough to accelerate our discovery of new chemicals and materials? Well, it depends on how we approach material discovery with automation and robotics. You can bring the automation and robotics in the lab and integrate it with the human scientists in different ways. So, for example, the human scientist can still be the main driver of the experimental workflow, and the human scientist can still define the problem, sets the conditions, and you can use robotics and lab automation to perform experiments. The human can still analyze the data and use some sort of data analysis and computer algorithms to guide the experiment selection. We call that piecewise operation. Or you can directly connect the computer and data science techniques to your automation tool. You get to something that's called semi-closed loop operation. Or we can even do the analysis automatically so that the automated robotic lab is directly integrated with your data science tool. Let's say an AI agent that can do the planning of your experiments. It can also analyze the data, and it can make the decision automatically what is the next experiment to do. But in this case, the human scientist is still the main driver of this experimentation technology that you have in your lab, and sets the goals. But this closed loop operation accelerates, or say, through the chemical space. And the last one is where the autonomous lab actually sets its own goals. It's self-motivated. It doesn't need any input from the human researcher. So where we are currently at is this autonomous self-driving mode operation that the human scientist is like a co-pilot to this robotic co-pilot to autonomously navigate through that infinite chemical universe. Now, with more advancements in AI, we eventually will move towards a self-motivated autonomous labs that can it can basically set its own goals and do its own autonomous experimentation campaigns. So basically, if you bring robotics lab automation in your lab and you automate the overall workflow and you use AI agents to analyze your data and make decisions about your next experiments, you can build this self-driving modality in your existing chemistry material science lab. And this provides an intelligent robotic co-pilot to the human scientist that has the potential to reduce the discovery time of new materials or molecules by a factor of 100 to 1,000. So for example, going back to the renewable energy example, if we can reduce the material discovery time from 50 plus years to them maybe less than 6 months, instead of tens of billions of dollars of R&D, maybe to $1 million. So you can see that acceleration factor due to this integration of human AI and robots. And when you reduce that discovery time, of course, we're going to reduce the chemical waste. This is a more sustainable way of doing research, and it also reduces the carbon footprint of your material discovery campaigns. And if you use scalable technology, the scalable reactors, you can also significantly reduce the time from discovery in the lab scale to market. So this is going to be a workflow of an autonomous lab where the human user defines the problem. Then you can use any sort of visual screening or computational techniques to down select potential materials that can fit the metrics that you have defined, or they have the properties, ideal physical, chemical, or optical properties that the human scientist is defined. And then through that visual down selection, you have a few potential targets where you don't know if you can actually synthesize them, if they are synthesizable, or if they're a good fit for your target application. Then you can feed those mutually selected materials to your autonomous robotic experimentation workflow, where you use closed loop experimentation with an end-to-end automated lab. And then you have AI agents for different parts of your autonomous lab. You can have an AI agent to do your precursor chemistry selection, retrosynthesis, controlling the conditions of your synthesis, and characterization of your target compound. And you can even do device measurements in a closed loop format. So within this digitalized material research framework, you can basically test the synthesizability, test your hypothesis, and you can even refine the materials selected through your visual screening. Now, at the end of the day, the goal is to reduce the time to solution by 100 to 1,000 times compared to the status quo of materials discovery. So the question then becomes, how can I design an ideal autonomous lab? Well, before going in the lab and automating every specific equipment in your lab to build an autonomous lab, you have to start thinking about what are the ideal traits of an ideal autonomous lab. Well, the first one, which is the most obvious one, is the material efficiency. You want to minimize your chemical consumption in your lab, and so that you can reduce the waste. And one way to do that is through miniaturization of your synthesis. The second one, which is very important for training of machine learning models in your self-driving lab, is the precision and reproducibility of your overall automation workflow. You don't want to introduce 50–80% variance in your experimental data. The third one, which is a key in building an autonomous lab, is in situ or online characterization. Depending on the type of material or molecule that you're synthesizing, you have to select the correct type of characterization that can automatically characterize the product coming out of your autonomous lab. And also thinking about when and how to do reliable automation is extremely important. The reliable automation here refers to how can you trust the data? Is the data noisy? How much noise you have in your experimental data? And then also thinking about the use of human intuition and knowledge, AI and robots, when and where they are needed in your overall campaign. It's not a good idea to just build a robotic lab because it's cool. You have to start thinking about the bottlenecks and the challenges of your existing workflow, and then start tackling those challenges instead of just automating everything in the lab. And then thinking about the modularity, reconfigurability of your automation, it's very important so that you're not just focusing on one single problem, and your autonomous lab is universal and versatile, and you can use it for a variety of different material classes. And then at the end, when you put all of these together, it becomes extremely important to think about how we can generate big, reliable experimental data. Instead of doing 1 or 10 experiments a day, how can we go towards 1,000, tens of thousands of experimental data a day so that we can provide these massive, reliable, reproducible experimental data sets for the AI agents of these autonomous labs so they can make better decisions? Because at the end of the day, the most important part of this autonomous lab is that intelligent decision making that augments human knowledge so we can more quickly navigate through that infinite chemical universe. So going back to that data, the big data, the choice of reactor in your autonomous lab becomes extremely important. So if you're synthesizing a material in a conventional flask, then you're going to be limited in terms of how many experiments you can do per day and how much data you can actually generate. And there are lots of other issues with these batch reactors. This slow, irreproducible heat and mass transfer rates. You have heat up and cool down and delay shutdowns. And it's really difficult to integrate in situ or online characterization tools with these batch reactors. So in order to tackle this problem, in my group, instead of using these batch reactors to address this problem of big experimental data needed for the AI agents of self-driving labs, we go from batch to flow reactors, and we basically use bespoke flow reactors to do our materials and molecular synthesis within our autonomous labs. Now, we borrowed this topic from the concept from microfluidics. Microfluidics field has been around for more than 30 years. It's not a new topic, but it's an ideal tool for an autonomous lab. And I've listed some of the key characteristics of microfluidics on the left here, but the most important one I want to highlight here is the intensification of reaction rate. So if you're synthesizing a material, or you're running an organic synthesis that is heat, mass, or photon flux limited in a batch reactor at a scale of 10 to 100 milliliter, when you go to a flow reactor, you can actually go from hours of reaction times down to a few minutes. So that acceleration enables you to run a lot more reactions a day. It can also significantly reduce your chemical consumption through miniaturization. So we go from tens and hundreds of milliliters down to a few microliter. And we can integrate our reactors with in situ or online characterization tools at the end of the reactor here. And then through precise automation, we can precisely control the reaction conditions, both continuous and discrete parameters. So if you put all these ideal traits together, we miniaturize the reactions and we intensify the rate of reaction, so we can do hundreds to thousands of reactions per day. That's hundreds to thousands of experimental data. That's your ground truth data. We call this intensification of data for AI agents of self-driving labs, and while basically minimizing the chemical consumption. So in my lab, we basically develop these bespoke flow reactors, and we integrate them with different robotic solutions like liquid solid handling for automatic precursor preparation. So this is a robotic solutions for precursor prep, and then we have bespoke flow reactors, and then we integrate those with our in situ or online characterization tool. And then we basically use an AI agent to drive this closed-loop autonomous experimentation to address the problem set by the human user and test the initial hypothesis set by the human user, so we can refine, revise, or even reject the hypothesis. So if I want to summarize what our autonomous flow reactors are doing, basically they are autonomously improving or self-improving the properties of materials that they're synthesizing. This hand-drawn sketch by one of my very talented students, Amanda, basically summarizes this concept. This was inspired by the statue of self-made man. You're self-improving the properties of these materials. So then in my lab, I basically use these autonomous labs that we develop using flow reactors as a foundational enabling technology. And then we use it for two different areas. One is nanoscience, where we basically build and deploy these autonomous labs to accelerate discovery of new nanoparticles and nanomaterials. The second area is catalysis, where we build and deploy autonomous fluidic labs to accelerate discovery of catalysts and ligands for fine and specialty chemical industry. And then in the third area, we use all the data and models that we developed in the first two trusts to basically study some of the underlying mechanisms of the reactions and processes happening in nanoscience and catalysis. Now, for today's talk, I'm mainly going to focus on nanoscience. So the material test bed for autonomous lab for the nanoscience applications is quantum dots. These are colloidal semiconductor nanocrystals that they emit light when you're excited with electricity or photons, but they have very unique and tunable optoelectronic properties. They can tune their emission color by tuning their size, composition, or even surface elegance. They are colloidally stable, which means that they have basically they have these long hydrocarbon chains attached to the surface of these nanocrystals, and that makes them colloidally stable in the organic solvent. And they have very narrow emission line widths, which means that you can have this variety of different colors by just tuning their size or composition. And they're very energy efficient. This is why they found a lot of applications in optoelectronic and photoelectronic devices. For example, in displays, in solid-state lighting, and even in emerging quantum information science technologies, and even solar cells. Now, an important point I want to highlight here is the difference between inorganic material synthesis and organic synthesis of small molecules. So when you're doing any sort of nanocrystal synthesis, there's a nucleation growth event happening within your synthesis process. Now, this makes it extremely sensitive to the processing parameters, how you heat, how you cool down your reaction, and what is the temperature profile of your reaction. When you do organic synthesis, you start with the same ingredients. Doesn't matter how you heat or cool down your reaction, you're going to get the same product at the end. Now, your yield and selectivity might be slightly different. But when you're doing inorganic nanocrystal synthesis, depending on how you heat or cool down, your monomer conversion rates are going to be different, your nucleation event is going to be different, and your growth rates are going to be different. So starting with the same ingredients, but just having different processing parameters, you're going to get to different products. The product here is the shape, morphology, and optical properties of your nanocrystal. So this makes inorganic nanomaterial synthesis extremely more challenging and difficult than just doing organic synthesis, because you have to also think a lot about the processing profile, your temperature profile within your reaction. Where when you're doing organic synthesis, you only care about the temperature, not the profile. So in today's talk, I'm going to talk about three aspects of an autonomous fluidic lab. I'm going to talk about the reaction miniaturization, automation, and process intensification through going from batch to flow. I'm going to talk about the importance of in situ online characterization. I'm going to show some examples of our bespoke in situ characterization tools for characterizing nanocrystals. I'm also going to talk about the importance of benchmarking the machine learning modeling and decision making of your machine learning agent driving your autonomous lab to enhance the performance and reduce the time to solution. Now let's just start with reaction miniaturization, the importance of flow reactors. The other reason that we prefer to use flow reactors than batch reactors for synthesizing materials is its unique characteristic of time and temperature to distance transformation. So when you run reaction in an autoclave or a batch reactor, time means just wait for a different amount of time in your reactor. But when you're running a reaction in a flow reactor, actually time means different positions along your reactor. This is the time to distance transformation. So by controlling the speed of these droplets moving along the reactor, you can have different reaction times along your reactor. And you can have different types of flow formats to run your reactions. You can have just all liquid, you can do gas liquid, liquid, and so on. Now, in addition to time to distance transformation, you also have temperature to distance transformation. The different positions along your reactor actually correspond to different temperature. So you can have this heating plates, and you can put your flow reactor, in this case, just Teflon tubing inside your heating plate. And you can have different temperatures or temperature profiles for each plate. So you can have these tunable heating profiles that are impossible to have in a batch reactor. And you can heat and cool down your reactors at a rate of 400 degrees Celsius per second, which is again impossible to have in a batch reactor. So in a sense, we basically have all these knobs to control all of these processing parameters. So you have this precise control over all of the processing parameters of your material molecule synthesis through these flow reactors. The other important trait of these flow reactors is their unique capability of integration or facile integration with in situ characterization tools. We can do spectroscopy, for example, and get a lot of information about shape, crystallinity, and size distribution, and even surface chemistry of these nanocrystals. So in my group, we use two different types of flow reactors for material and molecular discovery campaigns. One is the continuous multi-phase flow, where the materials or molecules are synthesized in these droplets or liquid segments as they're continuously flowing along the flow direction. And we use this for relatively fast reactions in the order of seconds, or when we want to do continuous manufacturing. The second flow format is called a single droplet, where we have a single droplet or a liquid plug of a reaction mixture. And instead of just continuously moving along one direction, you're just shaking this droplet back and forth in a very small reactor footprint. So this is great for discovery campaigns where we don't really care about the manufacturing aspect, or when we are dealing with relatively slow reactions in the order of tens of seconds or minutes or hours. And in terms of the hardware of the autonomous labs, we focus a lot on the modularity and reconfigurability of the hardware to make it as versatile and universal as possible, so we can make it multi-purpose, so we can apply it to different types of applications. So, for example, we have this plug-and-play format that we can have precursor formulation section that we can feed all of our precursors through these pumps and different streams. And then we have a mixing section, and then we have a synthesis module where the materials or molecules are synthesized in these droplets as they move along the flow reactor. We can then have different temperatures, different reaction times. At the end, we do in situ or online characterization for material synthesis. We do in situ spectroscopy. We're using the same spectrometer, but do two different light sources. We can do in situ UVs, near-infrared spectroscopy, or photoluminescence spectroscopy. And then having selective heating of the precursors is extremely important so that you can have access to different synthetic routes of these semiconductor nanocrystals. So this is why we have this modular design of the precursor lines. So each of these lines or tubing here is embedded within an aluminum module or heating plate, so we can selectively heat the precursors before they are mixed, before they go into the actual reactor section at a specific temperature. So here is where the precursors are injected, and we can selectively heat these precursors. This is our preheating module, and then this is the actual synthesis module. And at the end, when the product leaves the reactor, we can do in situ spectroscopy to characterize the product. And then the reactor plate is designed in a way that we can accommodate different reactor volumes within the same plate, so we don't need to redesign, remachine this heating plate. In situ spectroscopy, as I mentioned briefly, we have these bespoke flow cells. This is a stationary one where we attach to the end of the reactor, where you have your tubing going through this flow cell, and the product that is basically inside these blue droplets that's leaving the reactor goes through this flow cell, and we can do UV near-infrared absorption or photoluminescence spectroscopy. Now, if the reaction is fast, it's in the order of seconds. For example, when you're working on perovskite, metal halide perovskite quantum dots, you don't want to change the speed of the droplets because that changes mixing, and that's going to change the reaction environment within these droplets. We maintain this speed, or we are running these reactions at a constant velocity. We just have this mobile flow cell that moves along the reactor and can automatically detect different positions and do in situ spectroscopy at different positions corresponding to different reaction types. So by just doing this miniaturization of reaction and continuously running these nanocrystal synthesis in a flow reactor integrated with in situ spectroscopy, we can gain access to a lot of different data. So these are just two examples of synthesis of metal halide perovskite quantum nuts and actually doping these quantum nuts. I'm not going to go into detail about the chemistry here. I just want to highlight the amount of data that you can generate here. So in this example, this is just the band gap engineering of metal halide perovskites going from cesium lead bromide to iodide chloride through a halide exchange reaction. But look at the massive amount of data for the photoluminescence and absorption spectra that you can generate. This is metal cation doping of these nanocrystals. And then we can have access to millisecond reaction times. This is an ultra-fast reaction within only 2 seconds. But then you have massive access to massive amount of data, spectral data that you can then use to mine the data, train models in real time, and make decisions on the fly. So with this automation and in situ characterization, now we have access to this universe of quantum nuts. Now, the question is, how can we navigate this universe most effectively? So in the second part of the talk, I'm going to talk about how we can actually use the in situ generated data to make decisions on the fly. How can we automate that decision making so that we can have this autonomous experimentation modality here? So far I showed you that with flow reactors, we can automatically set the concentrations of our precursors. We have access to different precursors here, and then we can do rapid mixing, millisecond mixing times, and then we can do the synthesis in a flow reactor, and at the end, we can do in situ characterization. So we can automatically go from our input to the output. Then we can use all of our in situ generated data to train a surrogate model of our material synthesis process. You can use any sort of machine learning technique. You can use Gaussian process regression. You can use neural network ensemble to train a model of your material or molecular synthesis reaction. Once you have trained a model, you can use any decision-making policy. In this case, I'm showing a Bayesian optimization framework where we have used, for example, these 5 experimental data points, these black points, to train a model. The red line is the average prediction of the model. The pink area is the uncertainty of the model. And the dashed black line is the ground truth of the reaction that we are trying to learn with minimal experimental costs. Then in the Bayesian framework, we can use the uncertainty quantification and different decision policies. If you want to exploit the parameter space to automatically make a decision about what is the next experiment to run in order to navigate through the target objective that you have defined. Those could be the target properties, optical properties of the materials, or your goal could be, I just want to explore this space, learn the underlying synthesis structure process property relationship of this specific class of materials. But then the automatically selected reaction conditions are fed to the automated setup, in this case, the automated flow reactor, to run the next experiment. And then when a new data is generated, you go back into the loop and update your model, the new decision is made, and you just keep going through this closed loop autonomous experimentation until your objective is met or you finish your experimental budget. So this all sounds great, but the key question here is, what kind of machine learning technique can I use, and what is the best decision-making policy? Because there are hundreds of different ways of training a machine learning model, and there are hundreds of different ways of making decision on the fly to select the next experiment. So if you want to do this with your experimental platform, this is going to take you tens of years just to benchmark different machine learning modeling and decision-making policies. But this is where the high throughput nature of flow reactors becomes extremely handy, because you can use all your in situ generated data to build a digital twin of your actual physical platform. So in this case, we used more than 1,400 experimental data points of one of our quantum synthesis chemistries to train a digital twin of train a model, machine learning model, which is a digital twin of our flow reactors. And then we use this to use this digital twin. This is just a prediction accuracy, more than 90% accuracy of our digital twin. Then we use our digital twin to benchmark different machine learning modeling, different neural net architectures, and different Gaussian process regression kernels, and so on. And then we also looked at different decision-making policies, looking at expected improvement policy, upper confidence bound, probability of improvement, and so on. Hybrid policies. So basically, we did all of this through 600,000 simulations. And we did all of this within 1 month instead of tens of years of benchmarking. So in a sense, you're basically fine-tuning the brain of an autonomous lab or the AI agent of an autonomous lab. So after the fine-tuning of our AI agent, we integrated that with our automated hardware, automated flow reactor to do this autonomous closed-loop synthesis of these quantum dots. And this was like 4.5, 5 years ago, and we already showed that with the first generation of autonomous fluidic lab, we call it artificial chemist, we could autonomously discover the synthetic route of any target emission color of quantum dots within only 90 minutes if you treat the system as black box. And if you ask a highly trained chemist to do the same task, that takes 1 to 1.5 years to do it. But with this autonomous modality, we could actually solve the same problem within only 90 minutes. And after discovering a synthetic route, the setup can autonomously change its configuration to continuous manufacturing. So we call this an all-in-one platform because you can do R&D, discovery, and manufacturing within the same workflow. Here's a video of the artificial chemist searching through 60 dimension with 6-dimensional input, 3 outputs, and it's trying to find the synthetic route of the best green emitting quantum dots, starting with no prior knowledge. So this is just black box. Within 15 experiments or 90 minutes, they could find the synthetic route of the best green emitting quantum dots. And if you actually archive your external data and provide access to the prior data, you can go from 90 minutes to only 10 minutes. Later on, we upgraded the hardware. We wanted to show we can actually do multi-step synthesis. In this case, we have 2 flow reactors that we can synthesize, for example, green emitting quantum dots in reactor 1, and then we can do a band gap tuning in the second reactor through halide exchange reaction. And there's a lot of fluid dynamics behind here, how you can actually do reliable 24/7 operation here. I'm not going to go through details of that, but it's a very rich 3-phase flow dynamics here. And then in this case, we showed the 9 inputs, 3 outputs, and active learning. Again, using Bayesian optimization, they could discover the synthetic route of any target emission color within only 40 minutes. These are some examples of those autonomously synthesized quantum dots. These are metal halide perovskites, cesium lead bromide, chloride iodide, or mixed halides with different target peak emission energy or emission color. Here's a video of real-time operation of the flow reactor here under UV. That's why you can see the color of these quantum dots. And the first reactor is synthesizing green emitting quantum dots. The second one is doing a band gap tuning, halide exchange reaction. Now, depending on how much halide salt and what ligand you use, you can tune the target optical properties of these nanocrystals. You can go from green to red or green to blue. Now, most recently, we wanted to see if we can use our autonomous fluidic labs to discover the best-in-class quantum dot for a specific application. And we were interested in smart windows and solar cells specifically. There's one class of quantum dots called cation-doped metal halide perovskites that they're really good at absorbing deep UV light and then converting it to visible light and near infrared region, which silicon panels are pretty good at absorbing those, but they're not really efficient in absorbing deep UV. So our goal was, can we find the best-in-class metal cation-doped perovskite quantum dots for applications in the smart windows and solar cells? So to tackle this challenge, we basically designed an autonomous fluidic lab with 11 inputs, and in this case, we have 2 outputs. And the synthesis in this case is a high-temperature synthesis. We have to go to temperatures as high as 300 degrees Celsius. So we use stainless steel flow reactors here, and we use a specific type of flow format called segmental flow. We have an inert gas and liquid. So this is gas-liquid segmental flow with argon, and we pressurize the reactor so we can have this very uniform gas-liquid segmental flow. The formulation happens here with all of your precursors, the mixing here, the gas-liquid segmentation happens here. So you have very good mixing inside each droplet as they move through the reactor. And then this is where we do spectroscopy to characterize the quantum dot synthesizing flow. So here's a video of this operation, mixing, segmentation, and the synthesis happens in this high-temperature reactor that you can't see because it's thermally insulated. And here is the product leaving the reactor. This is a gas-liquid segmental flow argon liquid segments. This is cooled down at room temperature, goes through our in situ spectroscopy module, and we characterize the product. The data goes back into the AI agent. It updates its surrogate model, makes a new decision, and you go through that loop again and again until you run through your experimental budget. And then we did benchmarking of different decision-making policies. We looked at expected improvement, upper confidence bound, where you balance exploration, exploitation, and we also looked at pure exploitation. And we showed that expected improvement policy actually outperforms all the other policies. And in this case, we showed that we can actually have autonomously discover the best-in-class cation drop perovskite quantum dots within only 1 day that improves the total quantum yield of this specific class of quantum dots by 25% versus the best number reported in the literature. Most recently, we have shown that we can use the same autonomous fluidic lab to explore other type of material with lead-free perovskites. The same concept, you have the automated flow reactors for synthesis, you have formulation, synthesis characterization, and then AI-assisted decision-making for experiment selection. And here's a video of this flow synthesis and characterization. This is cesium copper iodide. And here the synthesis happens in this heated section. We go to up to 180 degrees Celsius. And then we cool down the product. And then it goes through our flow cell where we do in situ characterization. So those examples that I showed for quantum synthesis were mainly focusing on single or multi-objective optimization. 2 years ago, we got interested in the concept of going from this optimization to discovery. We wanted to see if we can have an autonomous machine that can discover a new chemistry. And as a test bed for this discovery problem, we focused on a specific class of semiconductor nanocrystals and a specific way of making these core shell nanoparticles or hetero nanostructures. That's called colloidal ALD, or colloidal atomic layer deposition. Where you can start with a semiconductor core, and then you can grow a shell around this core layer by layer. Now, each layer has 2 half cycles, and you have to wash your product after every half cycle. This is a very powerful technique because it maintains the size distribution of your nanocrystals. It improves the optical properties of these nanocrystals through passivations, and it can even introduce new optical or magnetic properties into your core nanocrystals. So it's very powerful, but it's very tedious and difficult to perform because you have 10 different layers, 40 different knobs that you have to tune. So it's a huge dimensional space. The high dimensional space, as I said, can go up to 40 different dimensions that you have to tune. And if you want to explore this space, just doing even a partial grid search, if you want to do 5 cycles of colloidal ALD, just with a partial grid search, you need like half of Earth of volume of precursor just with a partial grid search because the process is just so high dimensional. If you want to do 10 cycles, you need a precursor volume equivalent to Milky Galaxy. That's why not a lot of people actually want to tackle this problem. It's very, very difficult. So to tackle this, we designed a hardware of our autonomous fluidic lab to work with a single droplet format that they introduced in the beginning of the talk. But then we have this modularity that enables the hardware of this colloidal ALD setup to automatically have access to different precursors. So the setup can automatically select precursor 1, 2, 3, 4, 5, or so on. And then it can do any injections on demand. And then we have the synthesis module in situ characterization or even purification. But the most important thing here is that everything happens within only 5 microliter droplet. And everything is automated, so we can do up to 10 cycles of colloidal ALD. And we use just a few pumps to control the whole operation. So here we have our on-demand precursor formulation, and we can bring a droplet into a T-junction, and the setup can automatically inject into the droplet whatever volume of whatever precursor that it wants to inject. Here's where we do the synthesis of each half cycle. So here is a video of this droplet, single droplet, moving in our flow reactor, and we use pressurized gas, inert gas, to control the movement of this droplet into our flow reactor. And then we do in situ spectroscopy, and at the end we have purification. So we call this autonomous lab alpha flow because the dimension here is, as I said, 40 different parameters. And instead of using Bayesian optimization, in this case, we use reinforcement learning to navigate this high dimensional experimental space. where in the reinforcement learning, basically you're modeling the rewards of future actions that you take, and you have multiple different pathways that you can explore. So in this case, we let AlphaFlow explore this clear ALD chemistry for 1 month, 30 days of continuous autonomous experimentation. And what was actually interesting was after 30 days, it discovered a new way of, or new chemistry of doing plural ALD that was shorter, much more efficient than human refined chemistry after 15 years. So this is a very difficult multi-step chemistry. So AlphaFlow, within only 1 month, discovered a new chemistry that outperformed human refined chemistry. So the AlphaFlow chemistry is a human AI machine collaboration. This is an example of the power of this collaboration between human intuition, AI-assisted decision-making, and robotic synthesis for a very tedious, multi-step, challenging chemistry that we can accelerate discovery of new chemistries, new material, or molecules. We can also use this for organic synthesis if needed. And here you can see the optical properties and shell thickness of this clear ALD chemistry discovered by AlphaFlow versus human-discovered chemistry, starting with the same semiconductor nanocrystal core, but just following AlphaFlow versus human-defined chemistry. Now, after you discover your new chemistry, you can also ask the machine to do multi-objective optimization. Now, optimization is very straightforward with autonomous labs. Here it's showing that starting with different semiconductor nanocrystal cores, you can have different sizes of these cores. It can autonomously do multi-step optimization and multi-objective optimization and find the ideal processing parameters using the chemistry that it discovered on its own. So it not only discovers the chemistry, it also does the optimization within the same platform. Now, in terms of the throughput, we've compared the data generation throughput of AlphaFlow versus 1 to 100 scientists in the lab working 8 hours a day, 5 days a week. And as you can see here, the red line is the data generation throughput of our AlphaFlow single droplet platform, fully automated. In terms of chemical consumption, this is 100 times, 4 orders of magnitude more efficient. And in terms of chemical consumption, and in terms of the experimental data generation, it already outperforms 100 scientists in the lab. Now, you put reinforcement learning on top of this, you can get another 100-time acceleration on top of that. Now, the point here is not that the AlphaFlow is going to replace those 100 scientists in the lab, but the point I want to highlight here is that imagine every one of those scientists having access to one autonomous lab, and then here's an example of how much you can actually accelerate science and solving problems, challenging problems in chemistry and material science using these platforms. So what is next with autonomous labs? So the future of self-driving labs is definitely exciting and promising, but the most important impact of these autonomous labs is when we can have access to reliable data and reliable big experimental data. But how can we do that? We need to have a network of these autonomous labs across the globe. So how can we reach to that democratization of access to these very powerful research acceleration tools? So that's an engineering challenge for the next 3 to 5 years. I'm definitely urging the community to start working on more challenging automation technologies for chemistry, material science. And while we are developing new hardware technologies for these autonomous labs, we have to follow a specific benchmark, the standardized tests, so that we can report the reproducibility, reliability, precision, throughput, and optimization efficiency of the hardware and software of these autonomous labs, so we can benchmark these against existing technologies, and we can basically assess the reliability and continuous operation capability of these. But the other aspect is the cost, so we have to also work on reducing the cost of these hardware, so that directly ties with democratization of access to these very powerful research acceleration tools. So at the end, I hope I was able to convince you that these autonomous fluidic labs are great research acceleration tools as a robotic co-pilot to the human scientist. The human, you cannot remove the human scientist from the autonomous experimental campaigns. The human is like a human co-pilot to that robotic co-pilot that you have in your lab. And with these autonomous fluidic labs, we can reduce the time and we can close the time and the scale gaps in discovery, development, and manufacturing of advanced functional materials and molecules. So at the end, I want to thank all my team members, postdoc, graduate students, undergrads who actually did all the work I presented today. I want to thank my collaborators, Chris Reyes at Buffalo, Uchin at Brown, and the funding sources who paid for all the work I presented today. Thank you all. I will be happy to take any questions.